Alright folks, welcome to the last video of our module on our one-way ANOVAs. We are going to be running through an actual post-hoc test. So remember, post-hoc tests are conducted after significant hypothesis tests, and they're used to add clarity to those significant findings, because rejecting the null gives us a very non-specific statement that there's some kind of a difference somewhere in the populations. So if you remember, in the last video, we talked about two different hypothesis tests, and the second was what's called the Sheffa test, which involves essentially taking your initial data set, either drawing or creating two different groups, and comparing them to see if those two groups significantly differ. So we mentioned our anxiety score example, where we wanted to, again, take our three anxiety disorder suffering groups, lump them together into one group, compare them to our non-patients, and see if they significantly differ on our anxiety measure. So here's what our new hypotheses would look like, and we're not going to run through all 5 steps again. You'll see the Sheffa test borrows a lot from the original test. But our null is now just back to regular old mu1 and mu2. Mu1 is the mean of the population represented by non-patients. Mu2 is our clinical patients with our now 3 different anxiety disorders. They're all going to be combined together. The alternative hypothesis, of course, is that they are different. We would expect our non-patients to have lower anxiety levels, of course, but it would be worth knowing if they had higher ones as well. So we're going to leave this as a two-tailed test. So that's our setup here. And here's the thing about the Sheffa test. One of the reasons why it's relatively easy to do even by hand is that it takes most of its information from the original ANOVA. Notice at the bottom of the table here and over my shoulder here, we have the ANOVA table from the original hypothesis test, and we can see just how much is retained. We keep all the degrees of freedom the same, all the within stuff stays the same, that measure of typical error doesn't really change, our totals stay the same. The only thing that changes is because our groups are now different, our between groups measures are going to change. Our sum of squares between will be different, our mean square between will be different, and our F ratio will almost certainly be different. So we still use even the same critical value, which I've written at the bottom there. So we don't go look it up. We don't recalculate degrees of freedom. This is intended, by the way, to make it a little harder to reject the null and lower your chances of a type 1 error. But long story short, 80 to 90% of the stuff is just the same answers that we already got in the initial test. So here's what's going to change: our sum of squares between, our mean square between, and our F ratio. But here's the important thing. Remember how we calculated sum of squares between? We just subtracted within and total. If we did that here, you'd get exactly the same number. Wouldn't make sense to do that. So for the first time, we're going to have to calculate sum of squares between directly using a formula specifically intended for that. We can't just subtract anymore. So again, here we see our key figures. Here's how we did get the sum of squares between. Here's how we're going to get it now according to the book. So here's the first thing. I don't like introducing a lot of new symbols this late in the session. So instead, we are going to use symbols that are familiar, that we've used in previous modules. So G, for example, reflects the grand total, all of the scores added up in the entire data set. We've seen that before. That's just sigma x total across the entire data set. T reflects the total in each specific condition. We've seen that before. It's just sigma x squared for each of our groups individually. So here's what that same formula looks like when we again use the formulas that we've seen before. Sigma x for each group individually is squared, then divided by the number of people in that condition. We add them all up, then we subtract this total term. Sigma x total, all the scores added up across the data set, squared, and divided by the total number of scores. And then mean square we get the same way, F we get the same way. We're just going to be punching different numbers in. So here's what our new data set looks like. Notice our non-patients group hasn't changed. Neither has sigma x or sigma x squared. Now, these are the other 3 groups that have just all been combined together. We have sigma x's and sigma x squared for them as well. All of the total figures don't change. It's the same 12 scores, so they couldn't change. We don't even have to recalculate these. So let's calculate sum of squares between. Notice we don't have to get the other ones. We take the sigma x for each group, 32 here, 89 there. You square it, you divide it by the number of people in each group, 4 for the first group, 8 for the second, and then we use this total term, sigma x total squared divided by the total number of people in the study, which is still 12. When you plug this in and calculate it out, you will get a sum of squares between of 26.05. That's less legible than usual, but 26.05, again, unfortunately, it's sitting right in front of you. Then, just a couple more steps, got to turn that sum of squares between into a mean square so that we can calculate the f. And again, we've got our numerator here, our denominator here. We divide by 3, we round, we get a mean square between of 8.68. Turn that into an f ratio. Notice our mean square within hasn't changed, but this is how we get it. Turn that mean square between into an f ratio by dividing, and we get 3.86. There's 3.86 times as much between as within groups variance. So notice when we kept the same critical value, 4.07 is 3.86 across that line. No, it is not. It's pretty close, but horseshoes and hand grenades, it doesn't matter. It's not across the line, so it's not a significant result. So we failed to reject the null. Non-patients as a group do not score significantly different on anxiety than our clinical patients lumped together as a group. Even though the initial overall ANOVA was significant, this specific comparison is not. What do you suppose that you'd do in the real world if you got results like this? Well, what you'd probably do is run more comparisons. You would compare perhaps your non-patients to individual populations and see which ones they do significantly differ from. But when we make this specific comparison, all of our patients lumped together, again, it doesn't come out. That happens sometimes, even when the initial result is significant. So we want to probe this further and figure out where our significant differences are. But this specific test, we just had to recalculate sum of squares between, get a new mean square between, get a new f ratio. In this case, again, didn't come out, not quite statistically significant. So to recap the entire module, again, the ANOVA is intended for situations where we have 3 or more sets of scores, samples, to compare. You could use a bunch of different independent samples t-tests, would be kind of onerous and would increase the likelihood of a type 1 error. So instead we do them all at once by conducting these ANOVAs. We've learned about one-way ANOVAs. In the next module we'll learn about some other forms of ANOVAs, but a one-way ANOVA has only one independent variable or a quasi-independent variable. You have 3 or more groups, but they're only differing on one dimension, on one variable. If you had multiple IVs at once, you might use a factorial ANOVA. We're going to talk about that in the next module. But either way, the key statistic is this ratio of variances called an F ratio. The logic of the F ratio, again, is that treatment effects, the impact of the IV or the quasi-IV, are only going to show up in the numerator. So the bigger the ratio is, the more compelling evidence you have that your treatment is influencing scores. A high F indicates those condition differences are probably meaningful. There's a lot more variance than you'd expect based on the within group variance, which is sort of our representation of what natural variability in the scores looks like, so that we can figure out if the treatment effects appear to go above and beyond that. Again, the different steps. Step 1 only changes in that we're now accounting for 3 or more population means. Step 2 is now much quicker. We're just calculating 2 different degrees of freedom. Step 3, again, you might have to use the table in some classwork, but on an exam, you're going to be copying down a number I give you. Step 4, we have to get that F ratio. That takes a while. Again, we have all of these intermediate steps in the way. And then step 5 is the same as it ever was. Compare the test statistic to the critical value. If it's beyond that critical value, you reject the null. If it's not, you fail to reject the null. Okay. Next up, again, there is a practice hypothesis test and a post-hoc test available for you to review. There's homework assignments with some other material. There's, again, plenty of material in the book itself that will give you some additional questions on this. Make sure that you know the process for sure, and that when you choose this test, also know that for sure. But there will also be some conceptual questions on this material too on the next exam and likely the final. So continue on to the practice material. When you are done with that and you are ready to move on, you can start with the next module where we will talk about more advanced forms of ANOVA. Have fun. I will see you in the next module.